Hi guys, so today you'll be learning how to analyze your docking results using Primal and PowerPoint. This will work for any docking results from any software. In this case, we're using Autodoc Vina. And hopefully you'll learn a lot from this lesson. So to start off with, we're going to want to make sure we have the good version of Primal. I made a mistake. The educational version of Primal doesn't do some things and isn't as user-friendly, and the newer version of Primal, which while is a trial period, it does have many features that we need. So we're going to go to primal.org, and you'll just click download now, and you'll download the Windows installer. And it should only take about a minute. It's a pretty small file, and they got pretty good bandwidth. And then if you have the old EDU version of Primal, you're just going to add or remove programs after pressing Windows. Press Enter, and you'll search Primal. Uninstall whatever was there. Should be like a Primal EDU version or an older version of Primal. In any case, you'll run the installer. It's pretty simple. There shouldn't be any kind of issues you'd have with it, so I won't go over it. So the first step, some of you may have done this before, but for posterity, I will just show how to make a reference model. So I'll press my Windows key and type in Primal to launch the Primal software. And I will show this activation thing. You can just press skip. It's a little annoying, but it's worth it for the better version. Then I'm going to go to my files, my documents, my Crest folder. I'm going to do my docking results, PDB. Oops, wrong folder. Automated. Your scripts will look different from mine, but actually the first thing we need is to build our reference model. So we're going to click and drag our 1E8C over, and now we have our protein model. We're going to go to our teams channel, general antibiotic team, and we're going to look at the essential residues that we may have identified from our previous study, which are listed here. So what we're going to do is we're going to first show the different domains. So we're going to do select res ID, and domain 1 is res ID 1 through 88, so it's going to be res ID 1-88, and then we're going to click. You'll see these green dots, these red squares, and those show you all the atoms you selected, residues 1 through 88. And then you're going to click Action, Rename Selection, and you're going to name it Domain 1 and press Enter. And now anytime you click on this, you can show your selection. And right now we're just going to keep that color green. Next we're going to take the second domain, so select res ID 90 or 89 to pick up where the last one left off through 338. Oops, I spelled res ID wrong. And if you ever see an error like that, that's typically due to a small spelling error. So you're going to select res ID, Action, Rename Selection. Then you're going to name that domain 2. And then you're going to, I'm going to color this red. And then we're going to color domain 3, which is select res ID 339 to pick up where the last one left off through 497. And then you're going to click Action, Rename, Domain 3. So this means we have these different selections, so we can recolor them whenever we want. And we can change the representations, which is really useful for your reference model. Because the purpose of the reference model is to basically serve as a basis for which you'll analyze your drugs or your ligands that are binding to the protein. Because you want to be able to look back and see, well, where are the structures of binding, what's a good way to represent that, and is it therapeutically relevant? So now we're going to go to type in, I need to color domain 3, so this will be color. I'm going to color it yellow. Okay, so we have domain 1 is green, domain 2 is red, and domain 3 is yellow. Most proteins have separate domains, so it's always a good idea to color this separately. Now we're going to create our groups that allow us to see what residues are important on the structure. Obviously, those that interact with the product, UMT, are important. So we're going to type in select res ID 158 or res ID 185 or res ID 192. And this basically means it'll select any residue that is 158 or any residue, and I spelled these last two wrong. Or any residue that's 185 or any residue that's 192. It might be tempting to say and, but then that means there's no residues that are 158 and a residue 185. So that's why you got to be careful and always double check that your residues match with their ones on the chart. So now you see these red squares, and you can see that we can rename it. Action, rename. I'm going to type that, make this product residues, and then I'm going to show them as sticks, and I'm going to color them magenta. Actually, we're going to do color by element, then magenta. So that means it colors every atom that is carbon magenta. So that allows you to see the different like nitrogen groups and other heteroatoms, since heteroatoms are ones that form hydrogen bonds, and that's always useful. So next we'll find the residues that form important contacts with ATP. We'll do select res ID 4114 or res ID 220 or res ID 443 or res ID 116 or res ID 359 or res ID 465. Now you can see all these red squares where we look at our residues. We then click action, rename. This will be ATP. And then we're going to show as sticks and then color it by element. I'm going to color these orange. Actually, that's an ugly color. Let's color them cyan. So these are the cyan residues. Actually, you know what? I'm just going to color them something blue. And second thought, it's a good idea to color your residues that are like kind of background residues that are just kind of known structural features as kind of a duller color, so that way when you can highlight the residues later, the specific ones that are interacting with the drug, you can make them a bit more brighter and they'll pop more. So that's always good. And then we're going to select the invariant ones, which is select res ID 115 or res ID 118 or res ID 119 or res ID 182 or res ID 0, res ID 310 or res ID 341 or res ID 356. 115, 118, 109, 182, 210, 310, 341, and 356. So we're all good there. So these are the invariant ones. We'll name these action rename invariant residues. On this, we're going to click show sticks, and then we're going to color them preferably something a little more muted. We can color them purple. It's a little hard to see from it's enough of a difference from the ATP binding residues, but in any case, you're more than welcome to choose different residues than mine, or at least the coloring schemes. So right now we've shown all three domains, 1, 2, and 3, and we've shown our different residues. Those are our main residue groups, so we're all good in this count. So now we want to save our reference model. And to do that, we're going to go to our CREST folder, and we're going to create a folder that says Docking Results Analysis. We're going to double click on that, and then we're going to go to File, Save Session As, and then we're going to click our folder, and we're going to name it MER-E 1E. I forget. 1E8C. 1E8C docking. MER-E 1E8C reference. Click enter to save, and you'll see that it wrote to that path successfully. Now when you go back here, you'll see that you have this Primal session, and that means you can close out of this one and you can reopen it, and it will show your molecule that you made. And now we're going to use this reference model to analyze one of the drugs we found. But to do that, we first need to make a copy of this, so that way we always have this to look back to. We don't want to alter our original file. So we're just going to click Control V, Control C, then Control V to copy and paste. And then we're going to name this MER-E drug. I have drug 21, so I'm going to get drug21.psv. PSE. Now when we double click on it, you can see that we brought it up and it says MER-E drug21.pse, which indicates that you've chosen the correct file. Now we're going to go to our docking results wherever you have put them. Here's my receptor dockings. I'm going to click the drag, and we can see that it is now in our molecule. And we're going to click Show as Spheres. And it's a good idea to have your drug as a somewhat bright color as well that contrasts from the colors of your domains, so that way it's easy to see. And if you click on these arrows here, or you drag this bar across the bottom, you can see the different states of the drug. These are called poses. These are different ways in which each conformation of the drug can bind to the protein. And they are in order from the beginning to the end of binding affinity, with the beginning being the lowest binding affinity, which is the best. You want more negative. It's a confusing choice of terminology, but that's just kind of how it is. So from now, we need to see what all the states look like. So it's a good idea to always check and see how do all the different binding poses look if you were to view them all at once. Where does the drug bind on the protein in total? At this point, we're not concerned with how well does it bind, more as to where does it bind. To do this, we're going to type in split states, and then we're going to type in the word drug, and then as long as it's the first few letters of the name of your drug you're studying, you can press tab and it'll autofill the rest. And you're going to name it prefix. Then you're going to put, there'll be a comma, and you'll type in prefix. You don't have to add a comma, there should be one. Prefix equals drug underscore 21, and 21 can be whatever number your drug is, or however you choose to label it. And then that underscore at the end, you'll just leave, and it'll put a number after that to show you which state it is. And then we'll press enter, and it'll zoom in. I don't know why it does this, so you can just press and hold your right mouse button to zoom out, and then scroll down with 2 fingers on your mouse pad if you're on a laptop. Otherwise, use your mouse wheel on a 3 button, and you should see that you cannot see the rest. That kind of slices the protein so you can see through it if it was a much bigger protein. But now let's look at the overall shape of how these molecules bind. We can see that there is a cleft in between these 2 domains that it does bind to pretty well. And you can see that it also seems to interact with some of these ATP binding residues. There's this binding post here that's kind of in close proximity. Alternatively, there is this kind of lone pairs out here that are binding in between the red domain and the green domain. And if you only want to see the first 5, you can put your mouse over the selections and you can click and drag, and that'll turn off all but the top 5. And we can see that this particular drug likes to bind in between the clefts of the 2 domains. So that could be an important feature. Alternatively, and you want to turn off your original poses, which is what it split the states from. Each pose is called a state. Split states creates a separate selection for every pose, but it keeps the original. So why don't we just go ahead and delete that? You click action, then delete object. So now we have an interesting pose. It's kind of by the ATP binding domain. And then we also know there are some poses in the cleft as well as in between the red and green domain. Now it's always a good idea to consider the dynamics of the protein when you're looking into drugs. So we're going to go to dynamics.pit.edu. It's a web server hosted by the Bahar Lab, and we're going to click ENM 1.0. And then we're going to click Choose File, and then we're going to choose our 1E8C GNM ZSPDB. And now we'll click Submit. And in about a few seconds, you should see the web page update. It shouldn't take more than about a minute. But while we're waiting for that to load, I'll talk a little bit more about how to analyze these results. So for starters, I'm going to look at this pose 16. You can see the number 16 here, and that will correspond to what is in your docking log file. So 16 has a negative 6.5 affinity for negative 6.5 kcal per mole binding affinity. It isn't the highest ranked, it is number 16, but it's only 1.4 away from the top binding mode, which means in practice it might not bind to the spot all the time, but then again, the spot where it binds with the highest affinity isn't always the highest, isn't always the therapeutic site, and also it's dynamic and it can move between spots in reality. It's not static like is shown here. So that's an important thing to keep in mind. So now let's look back at that web page, and you'll see this structure pop up that shows the various domains and their mobility. And as we can see, we have that kind of core domain of our protein that isn't very mobile, and the red regions at the end shows that they are more mobile. And when we click on molecular animations, you can see that the way this protein moves, and for reference, you can see that they're in the same orientation now. The protein kind of opens like a claw, and it could be reasonable that it needs to open like that to let the substrate in, and then it closes and catalyzes the reaction. So with that in mind, we could say that these drugs that bind there, well, if they block this motion, maybe ATP and UMT can't get in as easily. It may fully inhibit it, or at the very least, it'll lower its kinetics. So kind of keep in mind the dynamics of your protein when doing any kind of drug discovery, because that's a really important thing to keep in mind. And it's something you can't just get from your static structure. You have to use the web server. So with this drug in mind, what we're going to do is we want to determine what residues is this protein making contacts with. So what we do is we click the command line, and we're going to type in select by res, B-Y-R-E-S, all one word, polymer within for of, and drug underscore 21 underscore 0016. And now we'll see we have a selection here that shows all of the contacts that this drug binds to. So any residue that has atoms within 4 angstroms, which is the kind of the maximum for intermolecular interactions to happen, will be shown with these these little red boxes. Now I'm going to rename it as drug 16 contacts. And from this, we can see that if we type in show as sticks, you can now see all the residues that they interact with. And we can color these as, I'm going to color them by element. Let's color them. It's always hard to choose colors. I'll color them cyan to match with the drug. So here now we can see all of the residues very clearly that bind with the drug. And now if we want to find what residues it forms polar contacts with, those will be residues that it interacts very strongly with. We'll click action, find polar contacts, then to any atoms. And here we can see that there are these kind of yellow dashed lines, and these indicate polar interactions between the drug and the protein. These are very strong interactions. These are very energetically favorable interactions. So they're very important to keep in mind. So I'm going to select these residues. You can just click on them one at a time, anywhere on them, and you'll see now we have a selection for them. They'll have the red boxes. We're going to type in action, rename, and we're going to type in, let's do drug and contacts. Since we're only analyzing drug 21 in this file, we can name this drug 16 because it will reference the pose, not the drug itself. And then I'm going to color these. I'm always running out of colors. Color element. I'll color them green. So, from this, we now have one of the poses analyzed. That's in an interesting spot. It binds to the ATP binding region. It's a relatively low spot, but that could give a low ranking spot, but it could give insight into how other drugs might be able to inhibit this protein by blocking those residues. So now we need to create a record of our results. So we're going to open PowerPoint. I'm going to start with a blank template. It doesn't need to be fancy. I'm going to name mine Bergen's insert a blank slide. Oh, content. I'm going to do a drug 21 overview slide. So what I'm going to do is I'm going to quickly hide my contacts so that we get back to our original reference model. It sticks. And then I colored the product residues magenta because sometimes they overlap, so you might have to go back in and recolor them if they got cut in another selection. ATP residues, those were blue, and then the invariant residues, those were purple. And there are additional sets of colors for the by element that have different coloring options. And then if you want to select all those ones that you and if you have any extras left over, you can just do and then you can hide the sticks. Oh, missed one. Hide sticks. Okay. And then we can just recolor the domains. So that's green, red, yellow. So we're back to our reference model. And then you recolor your sticks. I'm so sorry, it's been a long day. Product residues, magenta, and then HGP residues are, it's good practice at the very least. And then the invariant residues are purple. Okay, I apologize for that. So, and then we can turn off those dashed lines on and off by just clicking the selection. So we're going to look at all of them. And now we want to take a snapshot of this and put this in our PowerPoint so we can show the overall binding profile. So you're going to click display, background white, so display background white, and then you're going to click this draw/array button, and you're going to click draw. And this essentially allows you to create a higher resolution snapshot of the protein, which will be the size of your window that you can then click copy image to clipboard, and you'll see the image copy to clipboard, and now you can put that in your PowerPoint. And now we can crop it so it doesn't take up quite so much space. And we kind of want to note important regions. So let's make a circle so we can highlight certain things. You can make the fill transparent. The shape outline can be a higher weight. You can make it black, and then you can make it dashed so you can point to things. So there are three main regions that I kind of talked about that you might be good to point out. And we'll make an arrow. And the good news is you only have to make each of these once because you can just copy and paste them later on. Black shape outline, increase the weight. There we go. So for instance, that one, it interacts with and then another one, maybe change the color to make it a little more visible and a little bit of size. So we'll make it that's too hard to see. It's always, the colors is always difficult. I'll just make it blue. And then this operates at the interface of two dynamic domains. And we can other one could copy paste, and then this will be called make it purple. These aren't great color choices. You can fiddle it with yourself some more in your own time. And then finds in a cavity between two static. So now we'll enter the next slide, and this will be a little more detailed viewing of our first pose. So new slide, title and content, drug 21, pose 16, analysis. Now we'll re-isolate pose 16 and so we have our pose here, and now we'll reselect our residues within the range, and we're going to show them as sticks, and then we're going to show our polar contacts. If you want to see more, you can drag this little bar at the side over and you can see the longer names. And what we're really interested in are the ones that it forms polar contacts with. So what we can do is we can show our contacts, color, and I'm going to color it cyan, and then all of the rest aren't really relevant anymore. I apologize for having to repeat a step. As I said, it's been a long day. So now we'll show our contacts. And now we want to take like a decent snapshot of perspective that kind of shows the orientation of the drug and that residues interacts with well. It showcases its properties, but also gives enough of the protein's structure and references so that once someone looks at this, they know what part of the protein this is. So you click the draw. It looks smaller, but that's fine. You click copy image to clipboard, and then you can paste this in. And then you can crop it so that way it has a little bit more focus on the residues itself. I caught a little selections in there, but that's okay. This is just illustrative. Actually, we're going to crop it a little bit more. Okay, that's good. And then we'll make it a bit bigger. So we want to see what residues does this bind to. So we're going to do insert. We can take in some of our, we need to make a new text box. So we'll make it binds to ATP interact residues. And you can make this look much prettier on your own time. This is just a brief overview of what to look for. And now we want to know kind of what residues are we referring to there, to here. So we'll back to Primal. And if you want to view which residues are which, you can click on each of them in order from left to right. And you'll see tyrosine 470, tyrosine 357, and threonine 142. So what we're going to do is we're going to make a new little text box. We can copy and paste our existing one as a shortcut. And we're going to type in tyrosine 470. And it doesn't hurt to highlight it in the same color as the residue so it helps people know what's going on. Highlight, there we go. And then we'll copy and paste it, and then we'll do tyrosine 357, and then threonine 142. So then we can label these from left to right, and we want to make the fonts actually a little bit smaller so that way they don't obfuscate too much. Make sure it's consistent. Okay, so now we've labeled those important residues. And if you want, you can also label the ATP ones in a similar fashion. You want to color code them so they're visible. So maybe a dark blue highlighting with a white font. So this is kind of the general overview of how you kind of can analyze the results, and you can make it look a little bit prettier, but this is the kind of general idea. And later on I'll post like a more thorough analysis that you guys can look back to and compare on your own. But for the time being, I want to see what you guys can do and figure out by yourselves and see if you go down any interesting rabbit holes. So in concept, just look at the first, look at clusters. So when you look at your structure, you'll see that there will be lots of 20 binding poses, but they typically cluster in like a few areas. Like we kind of work through. So there's quite a few right there. So that's 9, and then 10 and 16, and 10 and 16, they both bind by the ATP residues, and then we have 19 and 20 that kind of bind elsewhere. You only really need to look at one characteristic binding spot in each cluster. So you can just look at 1 or 2 in the cavity, maybe look at 10 for a good binding spot by the ATP binding domains or residues, and so on and so forth. So take some like a creative liberty on how you analyze the results, and we can do a more thorough discussion in our next meeting. I hope you found this video helpful.